Thank you. Hello to the sparse remaining group. We'll have the final talk of the afternoon by Serkan Hosten on Symmetry adapted gram spectrum.
Hi, everyone. Thanks for being here on this beautiful day. I can see that you can do other things. I'm being here and then I'm listening to talk, but I'm glad it's going to be a short talk. It's going to be 30 minutes, and maybe we can even do it faster. We'll see. Okay. But on the other hand, I'll, please interrupt me. I'd rather have you sort of really get it than going, fast through this. So yeah, my name is Serkan Hosten. I'm from just across the bay, San Francisco State University. And what I'm going to talk to you today is joint work with two sets of people, Alex Heaton and Isabel Shankar. The work has already appeared. In the shorter version, actually, the archive version is more expanded, if you want to check that out. And so Alex and Isabel, Alex was a postdoc at MPI, Leipzig, when we were doing this, and Isabel was a PhD student here in UC Berkeley. They moved to their respective next jobs as a tenure track assistant prof and postdocs accordingly. And then Matthew Hyde was a master's student at San Francisco State, and then this was his master's thesis that we did together. So, this is a part of the optimization workshop. Just let me remind you a few things. If you're doing polynomial optimization, you a polynomial with real coefficients in n variables, and you're trying to minimize, you use this as an objective function. We all know that is a very, very hard problem. But one way of formulating it is, of course, instead of minimizing the polynomial function, right, you try to maximize the sort of a lower bound so that the difference is between the lower bound and the polynomial is non-negative. That's still hard. We didn't do anything new, but we can relax it, right? Instead of asking that polynomial to be non-negative, we can ask whether it's a sum of squares polynomial, right? So if polynomial is sum of squares, if it can be written, a real polynomial is sum of squares, if it can be written as a sum of squares of other polynomials, that's obviously non-negative, right? So the relaxation is easier, and it depends on the following observation. So classical, any polynomial p in n variables, I wrote it as p alpha x to the alpha. So x to the alpha is a monomial, right? P sub alpha is a coefficient. Let's say this is of degree 2D. It doesn't have to be actually 2D even, but let's say 2D. Yeah, any such polynomial can be represented, right, by a symmetric matrix. Okay, non-uniquely. There can be more than one symmetric matrix represents. Represents means you put the symmetric matrix in the middle, and then you have the monomial vector of monomials of up to degree d, if your polynomial is to degree 2D, and I just sort of multiply it out, right? And we know that this polynomial is a sum of squares if and only if the middle symmetric matrix is a positive definite matrix. Okay, and such a matrix is called a gram matrix. Okay, of course you realize that if I give you a polynomial of degree 2D and ask you, is this sum of squares, you can decide that by checking the feasibility of a semi-definite program. Right, the coefficients of your polynomial are written as linear functions of the entries in the Q matrix. They give you some affine constraints, and you want the Q matrix to be positive definite. That's exactly the feasible region of an STP. Yeah, and we can ask, is this STP feasible? I.e., is the feasible set non-empty or not? The feasible region of such an is for this problem. Right? So we start with a polynomial. Yeah, I'm going to call this gram spectrahedron of that polynomial. So spectrahedron is a generalization of polyhedra. Right? Polyhedra can be obtained by taking the non-negative orthant, intersecting it with an affine linear space. If you take the PSD cone instead of the non-negative orthant and intersect it with a affine linear space, you get what's called a spectrahedron. And these are special kinds of spectrahedra, okay, called the gram spectrahedra. And they parameterize for a given P, they parameterize all possible ways of writing this polynomial as a sum of squares polynomial. Okay, it's a nice convex set. As a very, very simple example, okay, here's a univariate polynomial of degree 2. Okay, you can ask, is this a sum of squares? Well, I presented for you a Q matrix in the middle. There's one choice. There could be more choices. It turns out it's a PSD matrix because I can factor it as an A times A transpose in the middle. So it's sum of squares. And here's the sum of squares representation. As I said, there could be more ways of doing that. And the totality of all of those is the Gram spectrahedra for this polynomial. Okay. So the big question is, for various reasons, we should study the geometry of spectrahedra in general to understand semi-definite programs, in particular Gram spectrahedra. Okay, the analogy here is that, you know, what has been going on for almost 70 years now, when people study polyhedra for the purpose of linear programming or integer programming, right? We know a lot more about polyhedra, and they help us for solving optimization problems. Now we should be able to do that now for these more general objects. But this work is in infancy, okay? Sort of kind of new. People have been studying, but not, you know, big results yet. Not necessarily, definitely not for general spectrahedra. And as you will see, for even Gram spectrahedra, there is sort of we're just slowly crawling. Yeah. Okay. So let me sort of show you one thing, that what I mean by studying the geometry. Okay. So let's take this binary sextic. Yeah, this is a polynomial, homogeneous in 2 variables of degree 6. Such a binary sextic can be presented by telling you 6 coefficients. Okay, so the coefficient of one of the monomials x to the 6 or y to the 6 we can assume to be 1. Okay, and everything else is whatever you want. Yeah. So if I ask you, if you want to decide whether this polynomial is PSD or not, sum of squares or not, okay, you have to construct this Q matrix, and the Q matrix in the middle has to look like that. Okay, so as you see that it has entries A1 through A6 coming from the polynomial, and then there has these 3 other entries, x1, x2, x3. So there is like a 3-dimensional space of representations. Okay. If I want this polynomial to be SOS, I want this matrix to be positive semi-definite. Okay, for some choice of x1, x2, x3. Okay, so if I pick one choice of A1 through A6, some real numbers, and sort of I hope that it's a sum of squares polynomial. If that's so, here is it's Gram spectrahedra. Okay, so it's a 3-dimensional object. It's convex. It's a convex body. It looks like a puffed up pillow, okay, or like a samosa, okay, yeah. So when I understand, sort of, it's a very simple object, but at this moment we want to understand this thing geometrically. Yeah. Like here, let me tell you, what we can say about this kind of stuff. So here's something that's sort of fairly new. It's a theorem and a corollary actually by Klaus Scheiderer. Okay, it says the following: if you have a homogeneous positive binary sextic, okay, I'm not sure whether you know this or not, but Hilbert sort of a long time ago has classified polynomials, real polynomials, which are non-negative if and only if they are sum of squares. Okay, sum of squares implies non-negativity overs, but the reverse is not true. And then Hilbert has this classification, and in the case of binary, okay, homogeneous polynomials, they are equivalent. So instead of saying SOS, I can say positive or non-negative there. Okay, so suppose you have one of those, and then you look at the Gram spectrahedron, that's G plus F. Okay, as you saw in the earlier picture, it's a 3-dimensional convex body. Okay, and in the inside corresponds to matrices that have to be 4x4 matrices of rank 4. Okay, in the interior. On the boundary, okay, this spectrahedron, it does not have any faces of dimension 1 or 2. Okay, it doesn't have patches of, it doesn't have these line segments or curve segments or or two-dimensional patches as faces. Okay. Moreover, it's a big question to decide whether a sum of squares polynomial, how many squares do you need to write the sum of squares polynomial? Yeah, and that's given by the rank of the points inside. So the lower the better, right? And for the binary sextic case, the on the boundary, okay, or on the inside even, the Gram spectrum has points, okay, can have points of rank 2. Okay, we know in general, generically, it's going to have exactly 4. Could have a little lower too. Okay, and moreover, yeah, here's a sort of a interesting corollary. Okay? If you have 2 of those rank 2 matrices on the boundary, okay, you can draw the line segment between them. That's in the Gram spectrahedron, but it never lies on the boundary itself. Okay, it's in the interior. Okay. And if you sort of, I don't know what your intuition is, but if you start think about it, the first time I thought about it, I said, well, it should be true in general, yeah. But as you will see, it's not true. Okay, and that's what I mean by studying the geometry of these objects. So, just a little result, you know, it says that if you have a binary sextic, okay, these rank 2 matrices, okay, on the spectrahedron, they can be read off from the roots of this binary sextic. Okay, so binary sextic has 6 roots, all complex, okay, and they come in conjugates of conjugate pairs. If you look at them, okay, by looking at those, you can write down a condition that says that those 4 rank 4 matrices that are on the boundary, okay, can actually lie on a hyperplane. Okay, so that's a generic picture. There are 4 sort of tip points here that correspond to rank 2 matrices. Okay, in general, they form a tetrahedron if I take the convex hull. But under this very special condition, they could lie on one hyperplane without the spectrahedron being 2-dimensional, still 3-dimensional. Okay, so that's what I mean by studying geometry. Here is another example. So let's go one more degree up. Yeah, let's look at binary optics, degree 8 polynomials. So in that case, we know, okay, that there are 8 rank 2 matrices on the boundary. Okay, for Sextics it was 4, for Octics is 8. I'll tell you the general version soon. So if you look at every pair of them, and then look at the line segment between them, it turns out those line segments actually lie on the boundary now of the spectrahedron. They're not in the interior anymore. And it's very weird that 16 of them, 16 pairs, they lie on the boundary and they form an edge, a 1-dimensional face of the spectrahedron. Now 12 pairs, they do not. They do lie on the boundary, but they do not make an edge. Okay, and moreover, these 16 edges and then 8 vertices or 8 matrices make up a graph, okay, which is isometric to the K44. Okay. So it's really interesting to try to understand this kind of geometry. Yeah. So here's sort of what you can do and on top of that. So let's take again a generic, you know, binary optic, sum of squares. What we can do is we can take the convex hull of those 8 rank 2 matrices. Okay, you get a polytope inside the spectrahedron. This polytope happens to be always a simplicial polytope. It's one neighborly, meaning every vertex is connected to any other vertex through an edge. Okay, and there could be many combinatorial types of this polytope, but in this particular case, there are only 2 combinatorial types. Okay. In particular, as opposed to the earlier sextic case, you can never make those 8 vertices lie on a hyperplane. Okay. So, and you know, we have some more generalizations in this direction for binary forms, but this sort of suggests that is there a way of comparing this polytope, this is inside spectrahedron versus the spectrahedron? Yeah, how close they are. Yeah, And the intuition is that as the degree increases, yeah, they sort of get close to each other more and more. Okay, so that's what I mean by geometry. Yeah. So let me switch gears. So this workshop is about optimization and symmetry. Yeah. So here what I'm going to do now is I'm going to take this could be any group really, but I'm going to do this for the symmetric group only for you. Okay, the symmetric group, of course, acts on the polynomial ring and n variables of degree d, yeah, the polynomials, by permuting the indices of the variables. Okay, that's the natural action. That is a vector space of dimension capital N, which is the binomial coefficient, n plus d minus 1, choose d. Yeah. So imagine you have an orthogonal representation, okay, for this action of your symmetric group. So they are given by these d sigmas, yeah, orthogonal matrices. What we can do is we can look at what we call the fixed point subspace of symmetric matrices. Okay, so that's either Sn to the Sn. So these are symmetric matrices, n by n symmetric matrices, capital N by capital N symmetric matrices, okay, which commute with all of the representation matrices. Okay. So why would you do that? Well, it turns out that these kind of matrices in the fixed point subspace, okay, they represent all symmetric polynomials. Right, so you remember every polynomial can be represented by a symmetric matrix. If the polynomial is symmetric, okay, there's always a Q from this fixed point subspace. Right? Okay. So great. So now comes an interesting thing, you know, that you would expect from representation theory. So if you take your fixed point subspace, okay, then there exists what's called a symmetry adapted basis. Okay, there is a change of basis T, okay, such that every matrix Q in your symmetric in this subspace can be represented in this block diagonal form. Okay, so the Q lambda 1 through etc. These are symmetric matrices themselves. Okay, and they are grouped according to, let me write this down maybe, according to the irreducible representations of your group. In this case, a symmetric group. Okay, so Q lambda 1, these are symmetric matrices, and the size of the symmetric matrix is equal to the multiplicity of the corresponding representation, and the number of copies you see is the dimension of the irreducible representation. Okay, so it really, if I look at this, you know, particular subset of Q's symmetric matrices, things sort of get easy. Okay, so how could it be useful? So let's take another example. This example is saying, let's take a binary quartic which happens to be symmetric. Okay, ask ourselves, is this SOS? Yeah, we can just forget about it being symmetric and then do it straightforward way. Yeah, so in the middle there's a 3 by 3 matrix, but if you say it's actually symmetric, then the Q matrix can be more specialized. Okay, so I can pick Q from the symmetry, from the fixed point subspace, and in it says there are two variables, so S2 is acting. Yeah, a matrix Q is going to be in the fixed point subspace if it's symmetric along the normal diagonal, but also it has to be symmetric along the anti-diagonal. Okay, which means that, you know, that certain entries, I color coded them, they have to be all equal to each other. So you reduce the number of variables. On top of it, you have this T, the change of basis, and all of a sudden your matrix is going to look like much nicer in this block diagonal form. So if you want to test that this matrix is positive semi-definite, you can test the blocks, which are smaller. Okay. So by the way, this is nothing new. You know, people have thought about these things much before. But now, what we can say is now the following. Okay, let's say I'm interested in the symmetric polynomials that happens to be SOS. Okay, what I can do now is I can look at the fixed point subspace Okay, those symmetric matrices that are fixed under this action, and which happen to be PSD. Okay, so I'm going to call that the symmetry adaptive PSD cone. Similarly, if I give you a symmetric matrix, symmetric polynomial, I can look at the symmetry adaptive gram spectrahedron. Okay, so that's the gram spectra intersected with the fixed point subspace. Okay, something much, hopefully nicer and smaller. Okay, so here's a picture to represent this. Okay, so the plane is the vector space of symmetric matrices of your choice. The blue cone is the PSD cone. The green hyperplane is a hyperplane given by a polynomial, maybe. Yeah, you intersect and you get the green ellipse. That's the gram spectrahedron. Okay, but then comes this hyperplane. That's sort of a grayish, greenish hyperplane, which is a fixed point subspace. I intersect. The intersection of the PSD cone is another sort of this cone right there. That's the symmetry adaptive PSD cone. Okay, and if you intersect it further with the gram spectrahedron, you get that red line segment, which is a symmetry adapted gram spectrahedron. Much smaller, much nicer. Okay. So, okay, so if that's the case, so what can we say now with those? These easier objects. As I said, this can be done for other finite groups too, but I'm just telling you for a symmetric group. The first thing is some structural results about the symmetry adaptive PSD cone. Okay, so the dimension of the symmetry adaptive PSD cone is that sum of those binomial coefficients, where m lambda I is the multiplicity of the irreducible component corresponding to lambda I, okay, of your symmetric group. Okay, so it reduces, as I said. Moreover, the extreme rays of your the symmetry adaptive PSD cone are determined by the rank 1 matrices in each block. Remember, they look like this, like these blocks. Okay, if you want to get a extreme ray, you have to pick, like this is one block, Q lambda 1 block maybe. You pick a rank 1 matrix there, and then 0 matrices otherwise. Yes, 5 minutes, yeah. Okay. Which is in contrast to the usual PSD cone, right? The PSD cones, extreme rays are always correspond to rank 1 matrices. Okay, in this case, you can arrange it to be that the extreme rays are going to be more than rank 1 matrices. Yeah? It's a nice structure there, but you just have to be careful. So let me give a few examples. Yeah, how it can be used. Let's take, for instance, a symmetric ternary quartic. Okay, 3 variables, degree 4, but symmetric. Such a polynomial can be given by 4 coefficients, really. Yeah, you don't need too many coefficients. So that's A, B, C, D. That's a symmetric ternary quartic. Okay, if you do that, yeah, if I'm looking at the symmetry adapted PSD cone, I'm sorry, symmetry adapted gram spectrahedron. Okay, it turns out that it's only 2-dimensional. It's small, and it's given by sort of in two pieces. Yeah, and you have to intersect these 2 spectrahedra on the plane. And what are those spectrahedra? They are given by actually one parabola, and it's interior, and a hyperbola, and then you pick one branch of it, and then it's interior. Okay, so this is binary. No, what was it? These are symmetric ternary quartics. If you erase symmetric, and if you look at the general spectrahedron, it's much more complicated. Okay? In particular, for instance, let me tell you this. Okay, if you take your F to be positive symmetric ternary quartic, in general, if you forget that it's a symmetric, the corresponding gram spectrahedron could have, okay, up to 63 rank 3 matrices on it. And that's the lowest you can get, and that's 63. There's a very beautiful algebraic geometry behind this. Okay, but when you do the symmetric, only 3 of them can survive. They could be complex, and 2 of them are PSD. Okay, and those are those intersection points. Those are vertices you see there. Those 2. Okay. So what you should imagine here is that I told you where was that? Oh, no, binary sextics, that was different. I didn't give you a picture of ternary cortex, whatever, yeah. So you can sort of tell a lot more, okay, because they are simpler objects. Let me see. So here's another one. This is symmetric binary sextics. Remember, I told you the non-symmetric version. It was this like a tetrahedron-like object. Okay? If you insist that's symmetric, okay, then it's again two-dimensional. Okay, and this time it's intersection of two parabolas. Okay, and it could have up to 4 rank 2 vertices. So what you should imagine is that we have the, what was that here? The puffed up guy, yeah? You intersect this with the symmetry, the fixed point subspace, and the resulting object is those intersections of these two parabolas. Okay, so almost done. Let me finish with the following two observations, yeah, two results. If you look at general binary forms, yeah, I always tell you about the cortex, no, sextics and octics, right? There is a general characterization of those points on the spectrahedron, not the symmetry adapter, the usual one, okay, of those points which are of rank 2. Okay, and these rank 2 representations can be figured out from the roots, some partition of the roots of your polynomial. And there are always 2 to the d minus 1 of them. Okay. And as I said, like what we can do is you can take the convex L of these guys and then compare to the spectrahedron. Okay, so this is sort of a classic theorem. Okay, but we can now extend this in the symmetric case. Yeah. So if you had the symmetric binary form of degree 2D, okay, we can tell exactly how many of those rank 2 matrices we're going to survive when you intersect with the fixed point subspace. Yeah. So if d is even, then 2 to the d over 2 is surviving, and if it's odd, 2 to the d minus 1 over 2 is surviving. Okay, and it's not just a number, by the way. We can precisely characterize which ones are going to survive by looking at the roots again. Okay? So it's like a nice generalization of a very classic theorem. Maybe I'll briefly say something like, you know, ternary sextics is a big spectrahedron, high dimensional. So we almost know nothing about it. We can look at the symmetric version of that. It's a 10 by, so the Q matrices are 10 by 10, and it's sort of broken up. If you look at the symmetry adapted basis, it's broken up into 4 pieces. Okay, one can hope to sort of do something with this, but even then it's difficult. Yeah, so we don't have much to say yet, at least. But you can now do some simulations, for instance. Yeah, you can say, hey, you know, if I look at the points on the boundary and classify the ranks of the matrices again, what do you get if I do randomly? Okay, so we did some simulations, as you can see. So those 4, 5, 6, 7, 8, those are the possible ranks. Okay, you know, there's not much of a pattern, but you do something. Like, for instance, most of the time you get in most examples you get rank 6 the most. Yeah, and it's not, again, it would be nice sort of to give explanations for these things from a geometric point of view. Okay. Let me stop there. Take questions.
Yeah, hi.
Yes.
So how do you, so in all your theorems, you have that you're requiring your binary form to have distinct roots?
Yes.
Yeah, so can you tell a little bit what happens when the roots are the same? So what happens to the spectrahedra?
If that, yeah, so then the spectrahedron basically degenerates to a spectrahedron of a lower degree binary form. If, yeah, so let's say, you know, if you're, let's say it was degree 10, yeah, and if some roots coincided, yeah, then you can sort of factor out that piece, okay, and then you look at the remaining part of your polynomial, and then that's what you look at. And that gives you still a spectrahedron, but a lower dimensional for a lower degree symmetric polynomial.
Oh, I see. So then, like, in a sense, this result is in a way general, because
general. Yes.
Anything else, like if you have the same
Yes.
roots, you can reduce it
That's
to.
right. That's right. Yeah, it's not, there's no surprises if you don't have distinct roots.
Oh, but then what happens if you have like two sets of roots that are the same, but like, let's say I have degree 10
Yes.
and I have two roots that are the same and one, and then two roots that are the same in the other way. This is different than having like just one set of the same roots. Is you can still degenerate to like smaller.
Say, but I mean, I understand the condition. So if you have,
Yeah, let's say you have like two roots 1 and then two roots 2, right?
so you have,
You can
okay.
still like
Yes,
reduce this.
yes,
It doesn't
yes.
matter that
It
the
doesn't
roots-
matter. It doesn't matter. Yeah.
Oh,
Yeah, doesn't matter.
okay. Why is that? Sorry, not immediate to me.
Because if you have the repeated root, right, that piece of the, so if you factor out, that is this, that's already a square, that polynomial, yeah? And I can,
Oh, I see.
I
You
can,
can say
I
that
can
these
get
are
rid
the
of it. I
factors.
can remove it, right?
You remove the square
Whatever is left
factors.
is governing the rest, yeah.
Oh yeah, because these are kind of like, yeah, I see.
And it
yeah,
doesn't
yeah.
have to be, I mean, this doesn't have to be symmetric. Any, any polynomial will work, right?
Right. So you just
Yeah.
care about the irreducible.
Exactly.
Okay.
That's right, yeah.
Have you looked at the case when f is not an SOS, but I don't know, lives in some quadratic module? Have you carried out the same analysis?
No, no.
Do you think it's much harder or?
I think it's harder, yes.
Okay.
Yeah. So if this, what you asked has not been done, like even for the binary forms, for the in general case, even, I have not seen much of it. If there is, one should look at it and then try to generalize it for a symmetric case.
Have you considered like fourth order tensors do the same thing as like doing these outer products?
No,
No.
no.
Also no.
I mean, it's so much to do. It's really start right now.
Yeah.
Yeah, no, I have not. I have
Okay.
not done that. It's a good question. Yeah, good question.
Any other questions in the chat, maybe?
Oh yeah, yeah.
No? Okay, well then, let's, next speaker again.
Thank you. Thank you.